Let's look at example 5. This one says, use Kramer's rule. That's your vocab to know that we're looking at determinants. We got to use that method to get full points. And bonus in this one, I only need to solve for z. That's it. So start by writing our three matrices, our coefficient matrix, our variable matrix, and our constant matrix. And now we need to solve for z, like the instructions said. So, using Kramer's rule, I'm going to do my special z determinant, where I replace the z column with the constant column, divided by the regular determinant. So, let's start with our special z determinant. I'm going to take the z column, excuse me, and I'm going to replace the z column with the constant column. So I got x and y stay the same. Replace the z column with my constant column. Check. Divided by the regular determinant of the coefficient matrix. Nothing changed. Now, these are 3 by 3 determinants, so they are a little more complicated than our 2 by 2 determinants. However, I want you to do something very specific. For dz, our top determinant, I would like you to solve this one using the expansion by minors method. So adding in our signs, and then doing the canceling thing, and solving from there. Then I would like you to find the d determinant by copying our first 2 columns over and doing our diagonal method. I would like you to practice both of them so that you know how to do both of them on your test if you want to check your answers. So, pause the video, use what you've learned so far in this lesson, use expansion by minors to do this one, use the diagonal method to do this one, and then take your answers up here to solve for what z would be. Pause the video and try that out now. Sorry guys, I just realized I made a major mistake. Let's go back real quick. I totally just read this as 3x minus 4y. It is not 3x minus 4y, that is 3x minus 4z, which means my coefficient matrix should have these flipped, which is going to change both of these determinants. So, when I replace the z column with my constant column, the x and y stay the same. So that should be a 0, so my x and y column are the same. And then that one should be a 0 for my constant column. And then for my regular determinant, those should be flipped. There we go. So that will change it down here. Sorry about that. And this one. So now pause the video now that we have all that fixed, and we can go back to trying that again. Sorry, guys. Let's check your work and see how you did. So for dz, I used my expansion by minors like I was supposed to. So I have a plus 2, a negative -3, which is a plus 3, and a positive -1, which is a -1. And then I did my canceling to get what's left, canceling to get what's left, and canceling to get what's left. And then I had a 2 by 2, so I just did the determinants from there to get -12. For my regular determinant, I did my diagonals method, tried to color code it all, simplified it, and I got -10. So -12 divided by -10 is 6/5. So I do not need to solve for the entire coordinate point for example 5. I just needed to solve for z because that's what the instructions said. So I'm done with 6/5. However, last example of the day, example 6, we just need to use Kramer's rule to solve the whole system. So I'm going to get you started on this one, and then I would like you to finish it. So first we have our coefficient matrix. Then we have our variable matrix. Then we have our constant matrix. And we need to solve for x, y, and z. So we need to get our special determinant x over our regular determinant, special determinant y over our regular determinant, and special determinant z over our regular determinant. So let's start by writing out what all of these are going to be. So for our special determinant x, I take my x column and replace it with my constant column. So the y and the z stay the same. The x gets changed. And regular determinant is just my regular coefficient matrix. In fact, I'm just going to fill that out for all of my denominators, because that is the same across the board. Now for my special y determinant, take your y column and replace it with your constant column. So the x and the z stay the same. The y column gets replaced. And then for my special z determinant, replace the z column with our constant column. So x and y stay the same. Replace the z column with your constant column. So really what we need to do is we need to find 4 different determinants here. We need to find dx, dy, dz, and d. So at this point, what I'm going to have you do is pause the video, and I'm going to let you use, these are 3 by 3s, so we can use expansion by minors or diagonals. You can use either method, whichever one you prefer. Find all 4 determinants, plug in your answers, and then solve for the whole system by the end. Pause the video, try this out using whichever method you want, and then come back to check your work. Let's check your work. So these are my final answers that I got. 1, 3, negative 2 is my solution to this system, so it's consistent, independent, has a single solution. For dx and dz, I decided to use expansion by minors, and for dy and d, I used the diagonals method. You're welcome to use those to check your work. If you got anything wrong, you can pause the video at this moment and check and see, try to figure out where you went wrong. But that is Cramer's rule. It's pretty nice. I think it's one of the fastest methods for solving a system of equations. It's also pretty unique. But remember, the key word that you look for to know this is the rule you use is it will say use Cramer's rule. That's how you know to write it out like this and use your determinants. So that is all for 6.6. That's our last method for solving systems of equations. In 6.7, the last lesson for this chapter, we'll be talking about an application for systems of equations. So, you are done with 6.6. You're welcome to start your homework.